Previously we talked about the magnetic field from just a wire, but a loop of current, as we've dealt with before, also generates a B field. If we have, some kind of loop, essentially a closed shape, but the current has to be coming from somewhere. So there might be a battery out here or something. But we have a current going through this loop, and let's say the current is flowing in this direction, this clockwise direction. If we consider this part of the wire, we could put our thumb in the direction of the B field, or in the direction of the current, and curl our fingers, and that's the direction the B field would be. It would be circulating the wire over here, and the same is true kind of as you go around. So from each part of this wire, the current in the middle or the B field in the middle, is going into the page. And as it turns out, the B field that's generated by this current loop, it is very similar to the B field generated by a bar magnet. So the B field is going into the page. So it's very similar to the B field of a bar magnet, where north would be maybe just below the page and south would be just above the page. And it creates that same kind of B field that loops around in 3D, just like the field of a bar magnet does. And again, if we think about what would happen if we added more loops to this, well, that would just be current continuing to flow in the same direction, and following the right-hand rule, it would still be into the page in the middle. So this B field is proportional to the number of loops in the number of coils in this loop, just like the magnetic torque was proportional to the number of coils when we put a loop inside an external B field. Now to demonstrate here, I've chained several batteries together so we can produce a stronger current, so that this coil of wire that I've created will have a more noticeable effect on the B field. So I have these wires coiled up. The positive end of the battery is over here, negative end's over here, and so there's current flowing, around this direction. Okay, which means if I follow that, follow the right-hand rule, current is curling in this direction, and so the B field will be pointing to the left. Okay, which means that it's acting much the same as a bar magnet, where the south pole is over here, the north pole is over here. Okay, and because of that, it will affect the direction of where the compass is pointing. This compass is sitting here, pointing happily to the north, but then if I bring it close to this loop, and I'll orient the loop roughly east-west so you can see the distinction, then the B field from this current will deflect the compass needle. There it is, happily pointing north. I bring it near the loop, and you can see that it swings around toward, not northwest, toward the west. If I move it back away from the loop, it swings back toward north. Here, let me turn around. North is more or less that way, and you can see it's pointing roughly that way. I bring the loop close, and the needle swings around more toward the west, according to the B field generated by this current loop. That north end of the compass points toward what would be the south pole, which is over here, and if I bring it over here on the other side, and again it points away from what would be the north pole in the bar magnet analogy to our loops of current. Now I mentioned previously that this guy called Ørsted, or something like that, Hans Christian Ørsted, discovered that a current produces a magnetic field. Now this guy Michael Faraday deliberately set out to determine if a change in a B field could produce a current. So Ørsted discovered that current generates a B field. And Faraday was trying to figure out if a B field could produce a current. So this is what he set up here. he had this little circuit here where he had a battery, the resistor, just so things wouldn't melt or explode, and then this wire coiled around a magnet. Okay, or it was an iron bar. It wasn't magnetized. It was just an iron bar. But iron's a ferromagnet, so it will align and all that. And then he had this secondary loop where that was just a wire hooked up to an ammeter, right? And so the idea was, if he flips on this switch, there will be a current running through this loop, and therefore there will be a B field generated. And so he wanted to see if that B field being generated would then cause a current over in this secondary loop, while there wasn't any charge actually being directly transferred between the circuits. So he's seeing if this B field produced a current, and it turns out that when he flipped the switch, right after he flipped the switch, the ammeter kind of went meh, and then went back down. And then when he flipped the switch off, it kind of did the same thing. And so what he came to the conclusion then was that it's not a B field that generates a current, but it is a changing B field that generates a current. Okay, just like it's moving charge that generates a B field, it's a moving B field, I guess you could, moving magnet, I don't know how to say it, moving B field or a changing B field that generates a current. Now, I don't have a setup like Faraday used, but I do have this solenoid, and I have magnets. Okay, so now if I take this magnet and I move it I move it into this solenoid here, there will be a changing B field that's passing through this loop, and if Faraday was right, that will in turn generate a current. Now, it only generates a current as long as the B field is changing. So it's not like I stick the magnet in here and then you can see the ammeter, it just kind of chills there. But if I move the magnet, around near the current, you can see that the ammeter, you can see the needle spiking around there. That as this B field is changing, it does generate a current through this wire. And it's not just like it's not just because I'm moving it, the ammeter needle stays there, but if I do move this magnet around in there, you can see that it does cause a current to be induced temporarily in the solenoid. If I move it quickly, then it spikes around. If I move it slowly, it doesn't move, the current doesn't move quite as much. But then if I just let the magnet sit in there, it settles out and nothing happens. So this, you can kind of see that this changing magnetic field does indeed induce a current in this current loop that is my solenoid. So a moving charge causes a magnetic field, and a changing magnetic field causes charge to move.